Hello, welcome dear students. Good morning to all of you and hope you all are absolutely well. So today in the current ongoing chapter of heat and thermodynamics, we are going to discuss about work done by a gas. But the question is how and when does a gas work? Basically during expansion a gas does work. Means when a gas is heated then it expands in volume, and in that case a gas does work, or it is said that work is done by a gas. But generally during expansion a gas does work externally, or it is said that this external work done by a gas. But why external? Now because during expansion of a gas it has to do some work against some external pressure or external agent, isn't it? Means some external agent or external pressure prevents its expansion. It is just like the inflation of a balloon or the bulging of a balloon. When we inflate or bulge a balloon by blowing air from our mouth, then the balloon expands or inflates or bulged, then it removes some air, but each and every moment the external atmospheric pressure tries to contract it. It means each and every time the balloon, isn't it, the balloon has to do some work during expansion, because it is expanding by removing the air in the space, because before blowing it was deflated, so there was some air. So when it expands it removed some air, but each and every time the external atmospheric pressure always works into play, and it tries and it prevents in its expansion. Don't let it to expand. So it has to do some work, it has to fight with external pressure, and to fight it has to do some work because it has to waste some energy. So it is just like that. When a gas is heated and it expands in volume, external pressure always prevents in its expansion, opposes its expansion. So to make the expansion effective or feasible, it has to do some work with external agent, we can say. We can just understand it by the external atmospheric pressure. To understand it or to simplify it. So that's why, since during expansion a gas expands and the external pressure always opposes in its expansion, so since it has to do some work against the external pressure, so that's why during expansion when a gas does some work, then it is always external work done, since it has to do some work against external agent. Clear? We may assume it external pressure. So that's why it may be called external work done by gas. So let's see the expression of external work done by gas. Now suppose this is a cylinder, and inside it there is a frictionless piston, and inside this cylinder some gas is confined with the help of this frictionless piston air tightly. There is no air inside the piston. So at such condition some gas is confined inside a cylinder with the help of a frictionless piston, that is a movable piston. This piston can move inside the cylinder. Since the gas, so obviously the pressure of gas on piston is P. Obviously since the gas, so it will exert some pressure on the piston. So the pressure exerted by the gas on the piston is let us assume it P. And the area of cross section, the cross sectional area of the piston, suppose is alpha, or you may assume any letter A, B, C, doesn't matter. So obviously since there is a pressure, the gas is exerting some pressure on the piston, so obviously there will be force on the piston by the gas. So we all know that pressure is equal to force per unit area. So force is equals to pressure into area. So this is nothing but pressure into alpha. Very clear. Now keeping the pressure at constant, it means if at constant pressure if we heat the cylinder, then what would happen? The gas will expand in volume, and since the gas will expand in volume in this portion, now in this portion gas is confined in this portion. This is gas. Up to this portion the gas is confined. So when we will heat, suppose by using a Bunsen burner, hair burner, we heated the gas. So the gas will expand. So as soon as the gas will expand in volume, it will exert, isn't it? It will expand in volume. So it will exert more pressure on the, isn't it, on the cylinder, and it will just, since it is movable, since the gas is expanding, so it will push the cylinder towards this side, and the cylinder will move from this position to this. And you can see this is a small displacement during heating of the gas. When the gas will expand in volume, it will push the cylinder towards the right side, and it displaces the cylinder to the new position, from this position to this, through a small displacement delta L, dl, sorry, okay, of gas during heating. So now work done. So now work done by gas, or the external work done by gas, we know that work done equals to force into displacement, and this is for small displacement dl, that is small work done dw equals to, okay, force into displacement, this is force, P into alpha is equal to force into displacement, that is dl. Okay, so P into dB. Why? Because area into length equals to volume. So since for small displacement dl, the small work done dw equals to dB. dB is the small change in volume due to small change in displacement. Now if the volume increases from V1 to V2, it means if the change in volume is not small, is quite finite. Okay, so in the case, the total work done by gas, if the volume increases from V1 to V2, where V1 is the initial volume, and if it increases to an significant value to V2, then in that case we cannot assume small work done for small volume. In that case, the volume will be from V1 to V2, not small. So in that case, we can easily calculate or determine the value of total work done by integrating the small volume, that is from V1 to V2 dW, that is P into V from V1 to V2. Now since, as I said, the entire phenomenon is happening at a constant pressure, so that's why, since P is constant, so that's why we'll have to take it out and outside of the integration. Then dB is equal to, then putting the value of dB, integrating, V means V2 minus V1, upper limit minus lower limit. So in that case, the expression of work done is equal to pressure into change in volume. So the work done by gas, or the external work done by gas, this expression is work done equals to pressure, that is constant pressure, into change in volume or increase in volume. Okay, so this is the mathematical expression of work done or external work done by gas. Now let's see what will be its graphical representation. Okay, very interesting, because we have calculated this expression by assuming constant pressure. But what will happen if the pressure is not constant? Because it is not mandatory that the pressure has to be constant. It will vary. So let's see. So in the first diagram you can see it is at constant pressure, but second pressure is at variable pressure, isn't it? That is variable pressure. Okay, so let's see. So in this case you can see along x-axis the volume is plotted, volume is plotted along x-axis, whereas pressure is plotted along y-axis. Now if the pressure is constant, then during expansion of a gas, okay, the graph of the work done by gas is thus parallel to the volume axis. This is the graph AB. Why? Because pressure is constant. Okay, pressure is not going to be changed. Suppose, and since the gas has some initial velocity, so that's why it is started from here. It cannot here. Here means volume is 0. So since initially there is a definite amount of gas, it has mass, so obviously it will have some volume. So this indicates it has some initial value. It has some initial value. So when V1 pressure is, suppose, what can I say, 10 Pascal, then change to pressure is same. So pressure is constant. So that's why it is straight line, just like the constant force, isn't it? Work done by a constant force. Since pressure is constant, so whatever be the value of volume, if volume is just continually increasing, but pressure is constant. Whatever be the value of volume, pressure is same. So that's why in this case, the graph of the work done by gas is a straight line parallel to the x-axis or volume axis. Now what will be the work done? How will we represent or express the work done by a gas through this graph? Now you can see the area. Now if we draw to perpendicular to normal or perpendicular to the two volume, this is V1 is the initial volume and V2 is the final volume. This means the volume increases from V1 to V2. Okay. So now if we draw to normal, then this rectangular square indicates this area This marked area ABCD represents the total work done by gas at constant pressure by the graph AB and and the curve confined by the confined. So the total area confined by the AB, the parallel line and the volume axis. So you can say ABCD, clear. It is just like work done by a constant force, which we have already discussed in case of the chapter work, power and energy, isn't it? The constant force and variable force. Now the next diagram, if the pressure is not constant, so what will be the graphical representation, or how can we calculate the work done by a gas? Variable pressure means pressure will keep changing. It is exactly just like the work done by a variable force, isn't it? So let's see. Now since the pressure is keep changing, isn't it? So now in that case, the graph will not be a straight line, it will be a curve, as you can see through the curve AB. Now in that case, how to calculate the work done by gas? Now in that case, since it is not constant, pressure is not constant, so we may, isn't it, divide, or we may resolve to a small stripe what we did in case of work done by variable force, isn't it? So we have just taken out a small stripe, EFGH. V1 is the initial volume, and this is a very small change in volume. We may assume it dV. So when initially its volume was V1, and in this stripe, small stripe, the volume is changed to V1 plus dV. So what is the change in volume? V1 plus dV minus V1, that is dV. So for this small change dV, what will be the work done? dW equals to P into dV. So in this way, we can divide the entire area through this equal, this small stripe, isn't it? For this small section EG, see this is very small, we may assume here, in this case, for this particular section, P is constant, isn't it? As I already said, in case of a car, if we take this small portion R, we may consider, since it's very small, so we may assume it as, isn't it, a constant or a linear, isn't it? So when we will, because we will not assume it as a curve. Since it's very small, we may assume it is straight line. So for this particular section, we will find out the work done by gas for this small section or stripe EFGH. Then in that case for EH, for this particular definite section, pressure is constant. For entirely it is not. So again it is applicable for the next stripe also. So in this case, we will get so many work done, and totally what we will do? Summation, that is integration. Then integrating or adding that all the stripes, we will get the total work done by gas, clearly. So we can see the total work done by gas is the curve, isn't it? Is the area confined by the by the pressure curve, that is the curve of the PV diagram and the volume axis, isn't it? This is the PV curve, isn't it, or PV diagram. So the work done by gas in case of a constant pressure or variable pressure, the total work done is generally expressed as the diagram of the area confined by the PV curve of the straight line and the volume axis. But here one thing you will have to remember, that during expansion, when work is done by a gas, and when gas does work externally during expansion. So since in this case volume increases, work is done by gas. So in this case, work is considered as positive. So these are the very important terms you need to remember. During expansion, when work is done by gas, since volume increases, work is done by gas on the gas is not factored. You just remember, during work done by a gas, it is considered as positive work done. Why? Since volume increases. So when work is done on the gas, isn't it? When work is done on the gas, means when we compress, isn't it? It is just like the the pressing, isn't it? The pressing or smashing, isn't it? The compressing someone's throat. This is called compression. This is expansion, and this is compression. So during expansion of a gas, it is work done by gas, its volume is expanded. So this is considered as positive work done. When work is done on the gas, in that case we will see what are the examples of work done by gas. Work done by gas we have already explained. We have already given its example, that is during bulging or inflating of a balloon. So what is the example work done on the gas? When we compress any gas. isn't it? Just like when we insert air inside the tire of a tube or of bicycle or any car, this is called work done on the gas. So during work done on the gas, its volume decreases, expansion so decreases, isn't it? So since the volume decreases, so in that case it is called negative work done. So when work is done by the gas during expansion, it is called positive work done, or when work is done on the gas, its volume decreases, it is called work done on the gas. Since first case volume increases, it is called positive work done, and the second case during work done on the gas, that is during compression. Okay, it means during work done by a gas, volume increases, this work done is called positive, and work done on the gas, volume decreases, it is called negative work done. And when heat is generally supplied from body to the surroundings, so in this case the sign of the heat is taken as negative. Why? Since from a system or a body heat is escaping, it means total amount of heat energy is decreasing, so that's why here heat is called negative. So here we will use the negative sign. But if the heat is supplied from surrounding to the body, so since heat is adding to the system, so its total heat energy will increase. So in this case, heat is generally sign is positive. So we have learned finally two things. Work done by a gas is positive, whereas work done on gas is negative. Why? During work done by gas, the volume is during expansion, work has to do some work. So volume expansion, volume increases, work done is positive. When work is done on the gas, its volume decreases, negative work done. Again, when heat is supplied from a body or a system to the surroundings, so heat energy is reducing, so here heat is taken as negative. Whereas if heat is supplied from the surroundings to the body, total amount of heat energy increases, so here in this case the sign of the heat is positive. Okay, hope you have understood. So we will see in next video.